refraction at the plane surface, we have to find the apparent shift in the position of the image. Suppose two media are separated by the boundary. Refractive index of media 1 is mu1 and of second media is mu2. And mu1 is greater than mu2. It means mu2 is the rarer medium. And if it is considered air, then its refractive index mu2 will be 1. And there is an object O which is at a distance t from the boundary. From O, we take two rays for image formation. One ray for normal incidence which meet at the point P, and this ray has the angle of incidence 0, so angle of refraction will also 0. It go in another media without any deviation. Another ray is taken which falls on the surface at the point Q and makes an angle I with the normal. This is the angle of incidence. Because we have taken mu1 is greater than mu2, so it will deviate away from the normal, and the refracted ray will be have the angle of refraction R. On retracing the refracted ray back, it meets the normal at the point P at point I. This is the image of the object. If we see that angle at O is the alternate interior angle and will be equal to I. Similarly, angle at I will also equal to R because these are the corresponding angles. Using the Snell's law, we can write that mu1 into sin I equal to mu2 into sin R. This implies that sin I by sin R equal to mu2 by mu1. If we consider that mu2 is air, so its refractive index is 1, and this is a denser media, so we can consider it as mu because now it does not require to use the suffix. Therefore, we can write it as 1 by mu. Now to find the value of sin and R, we consider that I and R are very small. In this case, sin I will be approximately equal to tan I, and this tan I will be equal to perpendicular by base, that means PQ by PO. Similarly, sin R will be approximately equal to tan R, and it will be equal to again perpendicular by base, this is PQ by PI. And substituting the value here, we will have that PQ by PO by PQ by PI, it is equal to 1 by mu, or we can write it as Pi by Po equal to 1 by mu. Therefore, distance of the image from the point P is 1 by mu of Po, or we can write that mu equal to Po by Pi. Po is the distance of the object, so it is a real depth, and Pi is the distance of the image from the point P, so it is the apparent depth. Therefore, shift in image closer to I will be equal to OI, and this OI will be equal to OP minus IP, and IP we have already calculated that OP minus 1 by mu into OP. If we take OP common, so it is 1 minus 1 by mu, and OP is the distance of the object, that is we have taken T, so it is T into 1 minus 1 by mu. So shift in the image position will be equal to delta T, and that is equal to T into 1 minus 1 by mu. We can write the expression of the apparent shift as delta T is equal to T into 1 minus mu to 1, where mu to 1 is the refractive index of media 2 with respect to 1. Here refractive index of media 2 is 1 because it is the air media, and refractive index of the denser media is mu. In case the ray travel from the rarer media to denser media, for example object O is at a distance t and a ray travels normally to the surface, so it pass undeviated. Another ray incident at an angle of incidence I, so it get refracted and bent towards the normal if mu1 and mu2 are the refractive index such that mu2 is greater than mu1. And on backward tracing the refracted ray, it meets a point I. This will be the image of the object O, and the shift is OI represented by delta t. So delta t will be, as we have stated earlier, that t into 1 minus mu2 1. Here mu2 1, it is the refractive index of second media with respect to 1, and second media is denser media, so its value is greater than 1. That means delta t will be negative. The image is formed in the opposite direction as in earlier case.